Thank you everyone for being here today. While we wait for more folks to join us, I'll just start with some housekeeping. The structure of this event will first be introductions, and then a program with Dr. Diana Dragomir, and lastly, some time to take questions and comments. If you have any technical difficulties, feel free to type it in the chat box, and I can assist you there. And if you have a question or want to make a comment, you can write it in the chat or the Q&A. You can also raise your hand to be unmuted if you'd like to ask yourself, and we will address those at the appropriate time. The James Webb Space Telescope has been jointly developed by NASA, the European Space Agency, and the Canadian Space Agency. The James Webb Space Telescope is scheduled to be launched on December 22nd, 2021. The Webb Space Telescope is planned to succeed the Hubble Space Telescope as NASA's flagship astrophysics mission. The telescope will provide improved infrared resolution and sensitivity over Hubble and will enable a broad range of investigations across the fields of astronomy and cosmology, including observing some of the most distant events and objects in the universe, such as the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. Please welcome astronomer Dr. Diana Dragomir for a special presentation about the James Webb Space Telescope.
Hi everyone, I'm happy to be here. I have some housekeeping too. I've done some of the panels before on Zoom, but I wanted to know, maybe Jessica can help. Can I interact with the audience at all? Like if I ask a question, will it be very kind of just clunky to get people to?
No, that's totally fine.
Would I have to raise their hand, or how should we do it?
You can raise your hand if you'd like to speak. You could write it in the chat and I can read from it.
Oh yeah, that works too. Yeah, I could also practice that later. All right, so I won't have too many of those, but I find it's always fun to try and see, like, get people to help participate. All right, so yeah, so my name is Diana Dragomir. I'm a professor at the University of New Mexico in the physics and astronomy department. And I'm an astronomer by training, though also a physicist. And my specific focus is on planets around other stars that we call exoplanets. So my work actually uses a variety of telescopes. But today I'm going to talk to you a little bit about this upcoming James Webb Space Telescope. So before I move on to the next slides, a little reminder that the launch date of the James Webb Space Telescope is currently set for no earlier than December 24th. So if you don't have Christmas plans, you can wake up early and watch its launch. But I expect a lot of us, I may actually be sleeping when it happens and hope to wake up and see hopefully a successful launch. But it may also be pushed back a little bit further, and I'll show you a little bit about how James Webb works, and hopefully it will be clear over the next this presentation why, you know, hopefully many things will be more clear, but also why the launch has been delayed for so long, or why it keeps being delayed. But it will launch. So let's start with a little bit of history, a little bit about space telescopes in general. Now, these three space telescopes are by no means the only ones that NASA or other space agencies have launched. But they're kind of the larger ones, most prominent space telescopes. So the Spitzer Space Telescope observes, we'll go over this in a few minutes, this kind of light that's called infrared light, similar to actually what James Webb will do, but we'll come back to that. And it was launched in 2003. It's actually still in space, but it was decommissioned, so it's no longer being used because of funding reasons. But it did observe for much longer than initially expected. Initially, it was expected to observe for just a few years, but it ended up observing the cosmos for 17 years, which is pretty phenomenal. We're hoping James Webb can do the same thing. Another another telescope that's been very useful is the Chandra Space Telescope. And the Chandra Space Telescope observes at X-ray wavelengths, so a very different kind of light. And I'm sure everyone's familiar. I'm going back into the past here, right, as you can see. And then Hubble is a space telescope that was launched in 1990. And it's still up. It's still working, just like Chandra. And it observes a number of different wavelengths of light. Ultraviolet, which we don't like to receive on the Earth's atmosphere. So that's actually one reason why Hubble is in space, because Earth's atmosphere absorbs ultraviolet light. And so if you use a telescope on the ground, on the surface, to observe ultraviolet light, you will end up not receiving much ultraviolet light, right? Because again, a lot of it is absorbed by the ozone layer. Very little of it makes it through the atmosphere. So if you want to observe that kind of light, you have to be above the atmosphere. Visible light and of course, infrared light. And of course, by the way, the Hubble Space Telescope is 31 years old, as you saw, because it was launched in 1990 and still working pretty well. Occasionally there are small issues that come up, but they almost all of them have been resolved from NASA centers with computers. And so it's been fixed whenever it's needed, except for a few situations where we have had to send astronauts to change out some of the detectors. And of course, early on to fix some of the focus issues with Hubble. Let's see. So Hubble orbits the Earth. So kind of like the moon, except it's way closer to us than the moon. It's orbiting the Earth every 100 minutes or so, once every 100 minutes. And this is actually quite different from how, as we will see, how James Webb will be orbiting in the solar system. The other thing, actually, no, I don't think I had anything else on Hubble, but I did, before I jumped into introducing James Webb, I wanted to see if there's any questions so far, because I want to make sure everyone is happy and keeping up. It would be a shame to lose people this early in the talk. Any questions to clarify anything so far? All right, I don't see any, so I guess it's going well. All right, so now I have a question for you. So why, since Hubble is still up and it's observing and it's doing so well, why do we need something bigger? Why do we need the James Webb Space Telescope? So one reason, well, I guess the answer to my question is actually right here. But let's see. So if the bigger the telescope, the more light it can collect from cosmological objects, stars, planets, you name it, anything that emits light, which is how we observe the universe, through light emitted by all of these astronomical objects. Anything that emits light, the more light we can obtain from that object, the better we can study it. So a good analogy is the bucket analogy. So if you put out two buckets and one has a diameter, so the size of the opening is smaller than the other. So the one on the right here is smaller. And you turn on the rain or the faucet. Let's say the rain because it's more uniform, and it rains for 1 minute. So the question to you is, which bucket will have more water at the end of the rain? Let's see if we can get some answers through the Q&A or the chat on this one. Should be a pretty easy question, I think, but any thoughts? No, it's a guess. Okay, I got a couple. All right, so people understand. Okay, that's good. So the one, yes, the larger bucket is the one that will collect more water. So similarly, the a larger telescope will collect more light. So when you're looking at very faint objects, you want something that can collect more light from those objects, because every photon of light matters. So this is a comparison of the size of the James Webb primary mirror. And as you can see, it's made of a bunch of little segments, hexagons. And then the Hubble mirror is a fair bit smaller, right? So James Webb is a couple of times larger than the Hubble mirror. And so we expect to be able to see, that's a good question. We expect to be able to see much fainter objects because we can collect more light from fainter objects with James Webb than we can with Hubble. And we'll see why that's important in the next slides. So I had a question in the chat here about why the beehive structure. So part of it is that it's difficult and very expensive, because it's difficult to make one giant piece of glass that will be 6 meters in diameter, like the James Webb. So as a result, it's also something that can be damaged a lot more easily. But as we will see, the way that the James Webb will be launched and deploy itself makes it such that if we had just one big mirror, that giant mirror would have to fly into space. So in terms of packaging it into the rocket, it's very complicated. You have to make sure, again, that no vibrations will break it during the launch. So both for launching, so for practical reasons, but also simply because it's very expensive to build one mirror of this size rather than combine multiple mirrors, which gives you the same effect, actually. For those reasons, this beehive assembly of mirrors was chosen instead of one large mirror. And we'll look at how that sets up, how that's planned to set up after launch at the end of the presentation. Okay, so the other big reason for James Webb, when we have JWST, other than the size and being able to see fainter objects because we can collect more light, is also the wavelength. So yes, Hubble can observe at infrared wavelengths, as we saw. And just a quick introduction, or more like a reminder, right? So observing something at visible wavelengths gives you a different image of that than at infrared light. So these are pictures of a crocodile and meerkats in visible light that we can see with our eyes. And this is the same image taken at infrared wavelengths. And so you can see different information, right? You don't necessarily see the color or the details of the meerkat or crocodile, but you do see where the heat emanates from. So you learn a little bit about where the essential organs of these animals are, for example, or in the case of the crocodile, it's underwater. So, it's a little bit harder to see. And you can also see just the way the heat is distributed in their bodies. Obviously, these are different kinds of animals, and so they'll look different in infrared light. Their organs and biological functions will be at different places. But even for biology, observing at different wavelengths gives you complementary information that you cannot obtain just by looking at just one wavelength. Let's see. Are you guys happy with me taking questions as I go? I don't mind doing that if everyone's happy with it. We might as well. Okay, good. So there's a question: if one of the 18 segments is damaged for any reason, can it be redirected so as not to corrupt the light from the other mirrors? That's a good question. I think in principle, the simple answer is that you should be able to still operate the telescope without one of the mirrors. But whether or not it's been set up from a software point of view for that to happen, I'm not sure. I suspect that yes, because, this could happen. But I don't know how easy it is to switch from 18 to 17 mirrors, for example. It may not be as easy as just kind of switching. Redirecting it is not really an option, because once it's assembled, you don't really get to move them individually anymore. Okay, I'll get to this later, but there's another reason why we can't move them. And if I forget to tell you, remind me. But I'll get to this when we look at how James Webb is going to be deployed. All right, so we're done with meerkats because this is a talk about astronomy, not animals. But let's look at this in context. So here's an image of the electromagnetic spectrum, as you may have seen in the past. And for context, we're showing here what the different telescopes are observing at different wavelengths. So you can see the visible wavelength range that we can see with our eyes is pretty narrow. And the Hubble Space Telescope can observe at those wavelengths, but also a little bit in the UV, just a little bit, and a little bit in the infrared. You can barely see it, but it's there. You get a little bit of infrared with Hubble. James Webb will observe a tiny bit of visible light wavelength range, primarily infrared. In fact, a lot of the infrared spectrum will be enclosed. And then the Spitzer Space Telescope, in its many last years, it didn't actually observe all of what's shown here, but initially, the first few years after launch, 2003 to 2008 or so, the Spitzer Space Telescope observed a kind of a infrared, but a little bit more infrared than the James Webb will. The reason that it's in the last years it did not observe quite so far in the infrared wavelengths is because it ran out of coolant. But that was planned. And James Webb also will run out of coolant after about 5 years or so. I think astronomers are hoping it will go longer. But one reason that James Webb is, it was really designed to work. Okay, so you might wonder what the coolant is all about. So the coolant, okay, if you want to observe at infrared wavelengths, that means you're observing essentially heat from astronomical objects. So what you really want is for nothing else in your instrument, including the sun. So nothing else should put in heat or infrared light in your telescope, so that when you detect infrared light from these distant objects, you know it's from those objects. So what could bring heat or infrared light in your telescope? Well, one very common way is if it's not properly shielded from the sun, and the heat from the sun can raise the temperature to just a normal temperature that we live at, right? So 273 Kelvin, or right now it feels like something like 40 Fahrenheit, but that's actually way too warm compared to the infrared radiation received from distant astronomical objects. So you want to shield the telescope from the sun, so it's basically very cold, and you also want to give it coolant that will artificially decrease the temperature even further. So the temperatures we're talking about here are 6 Kelvin. So if you're familiar with the Kelvin scale, 6 Kelvin is just 6 above absolute zero, right? Which is as cold as you can get. So that's really, really cold. But if you're not familiar with the Kelvin scale, basically minus 449 Fahrenheit. You can't imagine how cold that is. That's good, because it's so cold that I don't even want to think about it. But basically, you want to bring the temperature of the telescope that low, so that when it detects a tiny bit of heat above that, it knows it's from a galaxy or a distant planet, and not, for example, just its own instruments, right? The electronics themselves can produce heat. All right, let's see, we have a question here. Oh, no, it's a comment, great. All right, so let me show you how that is done. The coolant is not gonna be shown here, But here are two different angles of the James Webb. And so you've got the primary mirror and the secondary mirror. We'll see more of that later. But basically light from distant objects bounces off the primary mirror and then goes into the secondary mirror, which then sends it into this little hole here, which is where the light goes to all the various instruments, because the telescope itself is not all that there is. There's more to it. That'll come up on the next slide. And so the observing side is here, and then the sun, and then this is basically the sun-facing side. So the sun is, depends in this left side image, if you think of below, what below is in this image, that's where the sun is, below the telescope, right? And then the right-hand side image shows the view from below. So this sun shield is going to play a huge role in blocking light from our own sun from reaching the detectors and the telescope, so that we can be sure we're observing the very, very faint infrared light from distant objects instead. So that's already a pretty big engineering, I don't want to say complication, but it's one of the reasons why people are so careful with every step of building James Webb. Well, it's built now, obviously, but you want to make sure that all of a lot of the shield, so this kind of shield is new technology, and you want to make sure that all of this is done correctly, because you don't want to end up in space and then realize that there's too much heat and you can't actually see your galaxies or planets despite the large telescope. Okay, so I said that the telescope is, and the shield is not all that there is to it. There's also the solar power array that you can see on the right below, thankfully facing the sun. So it's shielding the telescope from the sun, but we do want to charge the batteries of James Webb because there are electronics that need to function. And for example, sending information back to Earth, like the images is going to take. And the other things that are on board are detectors, right? So when you, the best analogy is like, if you have like a DSLR, one of those big cameras, the lens is the optical part, that's the telescope part, but inside, just like in your phone, there's a CCD, right, detector, and that's where the image is actually, the image is taken there. So back in the day, it used to be film, now it's CCDs, right? Well, James Webb has CCDs as well. It actually has a number of them. So let's take a look at how large the field of view of those CCDs are. And they're all very different. There are actually 4 sets of them: near spec, near cam, nearest, and MIRI. And they all stand for a combination of imaging and spectroscopy. By spectroscopy, we mean observing on multiple wavelengths at the same time. So you can get a spectrum of what you're looking at. But you can also see that the amount of sky that any of those instruments can observe is a little bit different also. So it's not, they all have different capabilities in terms of the wavelengths, the exact wavelengths they can observe at, but also how much sky they can observe and what the shape of that field of view is. All right. So that sums up what I wanted to say about kind of the technology and sort of the motivation for why we need James Webb. Let's look at the main science themes that James Webb was built for. So there are 4 big science themes. One is understanding the beginning of the universe. And for this, and this is actually kind of linked to the second one, which is the formation of galaxies. Those 2 go hand in hand. And the beginning of the universe, there's a little bit of heat that we can still detect from the beginning of the universe, but that heat is so faint that until now, until James Webb, we have not been able to detect it with current instruments. Again, because we haven't been able to make those instruments both cool enough so that we can detect the heat from the beginning of the universe over the noise of even just the instruments, and also because there hasn't been a telescope large enough to do that in space, right? You cannot do this from the ground. It's way too hot on the ground. Forget it. You have to go to space where it's cold, have a shield, and also have coolant that will bring down temperature. So you need a large telescope in space, and James Webb is the largest, coolest telescope in space to do this. can take a look at what we mean by, well, just at least the science of the beginning of the universe. Let's see. Okay, I don't see any questions. So very briefly, the way that the universe / the galaxies started to form about 14 billion years ago is that initially the universe was just full of hot gas, very hot gas. And that's called the beginning of reionization. You don't need to know what that is in detail. Initially, there were a number of just stars that formed without galaxies. Today, of course, we have the structure, right, of galaxies, and inside galaxies are stars, and we don't really see any stars that are free floating outside of a galaxy unless they're inside their own galaxy. But 14 billion years ago, that's what happened. Stars formed first, and then they came together into galaxies. Galaxies grew, became more massive, and eventually initially they were kind of all touching each other, but then they just kind of split into each of their own galaxy and continued to live that way. But the details of how all of this happened are actually, we understand some of them, but we don't understand all of them because so far we haven't been able to observe far enough into the history of the universe to understand how this very beginning of the galaxy, star and galaxy formation happens. So with James Webb, we'll be able to look all the way to the beginning of, very close to the beginning of the universe, and especially observe the first galaxies. And how do we do that? How do we go back in time? I didn't really talk about this very much because sometimes it can be a little boring and I just wanted to get into it. But the most distant objects in the sky are also the most distant objects in time. We start with the idea that the universe started from a point and expanded to what it is today. So that means that things that were formed early on are now at the edges of the universe. The universe doesn't really have edges. It's okay. I can't visualize this either, right? This just, we know this is true, but sometimes we have to accept that there are things about the universe that humans can understand without actually being able to imagine them. So you have these galaxies from early on that are now very far away from us. The question of whether they still exist is a good one, because the light we receive today that we see with our eyes when we look up in the sky, or our telescopes, because our eyes are nearly strong enough most of the time, the light that we see with our telescopes is very old light. It's just getting to us now, but it's light that began its journey at the beginning of the universe. But we need Webb to actually see the light from those very first / more distant, it's kind of the same thing, galaxies. And we haven't really been able to see light from those galaxies until now, because we haven't had telescopes that were both large enough and cool enough in space to detect essentially the heat from the beginning, from galaxies at the beginning of the universe. I see a question. Okay, great. Wait, did someone say it was boring? Come on. Any questions so far? Any other questions? All right. So I'll keep an eye on the chat also in case there are any. Let's take a look at this image now that is called, you may have seen this before, it's called the Hubble Deep Field. It's actually just a part of it. So this is one of the images, the deepest, right? So furthest in time, in a sense, images that the Hubble Space Telescope has been able to see. So Hubble basically picked a part of the sky, or astronomers did, and it stared at that piece of sky for a long time, collecting light. So if you're not large enough to collect lots of light, another way you can do it is by staring longer, right? So if it rains longer, eventually the small bucket will also acquire as much or collect as much rain as the large bucket would have after just 1 minute. The problem with that is that at some point you have to stare for so long that, it's so much better if you have a bigger telescope, because you can stare for less time and get the same amount of light, and then you can actually move on to something else and study something else in the same amount of time. Anyway, so Hubble stared at one part of the sky. I don't remember exactly how long it stared at this piece of the sky, but when the image came out, basically, it showed all of these galaxies. I think in this image there's one star. Wait, two stars. Right. Can you help me find the stars in this image? You might have to I don't know how you could do that. You have to kind of tell me what corner they're in. Give it a shot. So there are two stars here and the rest are galaxies. Find the stars, go. So it's fun to kind of see how we identify things, right? Okay, lower right. How can you tell? And top right? You sure? How can you tell the lower right one? Diamond shape. Yeah, right. So there's a star that has this cross kind of superposed on it. Yeah, top left also, exactly. And then there's another one kind of in the top left that also has this cross. I'm not going to get into why, but I'm happy to talk about why that is later. But galaxies don't do that when we observe them. Okay, so moving on. Oh, there was a Q&A too. All right, cool. Okay, so if we look at more or less the same part of the sky, I'm going to transition now. So memorize this image because we're about to switch into what James Webb would see if it was looking not at the same part of the sky, but galaxies are distributed evenly throughout the sky, right? So you can imagine it's the same part of the sky for practical purposes. And this is what James Webb would see because it's so much bigger. So now you have a ton of galaxies, but every little point, I should have said that for the previous one too. Here we can go back. Every little point of light here is a galaxy, other than the two stars that we just saw, right? Every tiny, tiny point of light that you can see, that's a galaxy, cannot be anything else. James Webb will see many, many more and see the ones that are closer and brighter, see them even better and help us understand more about them. But basically we'll be able to look further into time and distance all the way to the first galaxies and help us understand how those stars that were floating around free eventually assembled into galaxies, which is something that we know they did, but in terms of how exactly that happened and over how much time, for example, relative to the history of the universe, we just don't know. All right, so I'm gonna move on now to my favorite topic because it's what I work on. But you see how basically James Webb can really help, is going to serve a wide range of astronomy. So starting with the early universe to understanding the earliest galaxies, to understanding formation of current galaxies. Galaxies are still forming today, not that much, but some of them still are. And I'm gonna skip the formation of stars for time reasons and go straight into understanding exoplanets. So here's a cool video. I hope everyone can see the video. And I'm also hoping I'll lower the volume just in case. Let me pause it for a moment. So what we're looking at here is a simulation of a planet around another star. And from our point of view, we're seeing that planet cross the disk of the star. So when that happens, so I should say that we're not actually seeing the planet cross the disk of the star, but that's how you can imagine it. And what we actually see is the brightness of that whole system, star plus planet. Its brightness is steady. And then when the planet passes in front of the star, the brightness dims a little bit. And that's what you can see here beginning to happen. And that dimming is because the planet is basically casting a shadow onto the star, blocking out a tiny amount of light. So again, we don't actually see the planet. It's very hard to do that. These stars are so far away that there's no telescope that can separate the planet and the star. What we do see, though, is the effect of the planet passing in front of the star. And that is called a transit. And so you get this transit let's see, all the way to almost the end. Oops. All right, just play it again. It went too fast. All right, stop it here. And then the different colors are the same transit, but observed at different wavelengths of light. And so we can use the fact that the transit, the dimming of the star, what we call the transit depth, is different. So the amount by which the star dims is different at different wavelengths. And that's because the planet's atmosphere is absorbing different amounts of light at different wavelengths. So essentially, that's how we get a spectrum of the planet's atmosphere. And by measuring the transit depth at different wavelengths, we can say something about what is in the planet's atmosphere, because we know what kinds of molecules and atoms absorb light at different wavelengths, right? They don't all absorb light at all wavelengths the same way. So let's take a look at what that looks like. So let me just finish this video for you. It did kind of show it. So you can see the different amount of dimming, the different depth. So that's basically the brightness of the star over time. And we then take that data and make a figure as a function of wavelengths, as you can see here. And here's the light, amount of light blocked, okay? And here you can see that at different wavelengths, if we see at, for example, 10,000 nanometers, at which James Webb can actually observe, if we see a deeper transit or a spike in the spectrum, that means there's ozone in that planet's atmosphere. It's actually pretty straightforward when you think about it, how we do it. But seeing these peaks stand out over the noise at the bottom is very hard. And so you need a large telescope to collect a lot of light for us to see this clearly enough. For Hubble, a spectrum like this might look like just kind of noise all over. So the signals would just be buried in the noise because we're not getting enough light because Hubble isn't large enough. The kinds of things that we'll be able to see in exoplanet atmospheres are like shown here: ozone, methane, water, carbon dioxide. And these are things that we're also interested in because in the right combinations, they might be indicators of possible life. I say possible, okay? We're a long way from being sure of finding life on exoplanets, but that doesn't mean that it's within reach potentially with the James Webb Space Telescope if we can detect the right gases on these planets. Now, I don't actually know how I'm doing for time. I should probably check. But I'll just keep going because I'm almost done anyways. But one thing that I am working on with James Webb, once it launches and begins observing, is this lava planet. So I just wanted to show you a picture. But before I go any further, let me remind you that this is not a real picture of the planet, right? So remember, we only get this kind of indirect evidence of an exoplanet being there because we see a transit. But just because it's indirect evidence doesn't mean it could be something else. We are pretty sure from things like the size of the planet, nothing else the size of an Earth, for example, could cause a dimming like that. So we know that those exoplanets are real, they transit, right? And so we can learn from the transits a lot of things about what they're like. And so from this information, we can imagine what that planet star system might look like. And so this is an artist's conception based on real data. And this is actually a super Earth, which means it's a planet a little bit larger, about twice as big as the Earth. So you might think, oh my gosh, that's so different. But the real big difference here is that this planet orbits its star in 18 hours. So take a moment to remember that the Earth orbits the sun in 365 days. This planet orbits its star in just 18 hours. What that means is that it's really close to the star. It's actually only 3 times the distance between the center of the star and the edge of the star, you put another 2 of those distances next to it, and that's where the planet is. It's really close and it's really hot. Okay, so 2000 Kelvin or 3100 Fahrenheit. This is probably a lava planet. The whole planet's surface is probably molten, or at least the planet, the side that faces the star. And it's been a very intriguing planet for astronomers because it's doing a lot of different things. For example, we think that a planet this hot cannot have an atmosphere because the star would have vaporized it away ages ago. But we have evidence that this planet does have an atmosphere. And we're trying to understand how that came to be. It's really pretty spectacular. And one of the things that we're going to do with James Webb is observe its atmosphere and see what it's made of, so we can better understand how come it has one in the first place. So that I'm pretty excited about this data specifically. But there's a lot of science, as we've seen, that will be done with James Webb beyond. This is just one of many proposals that have been accepted and that will use James Webb, and that's just in year 1. It's got at least 5 years of coolant, and so at least 5 years of awesome science. Okay. Kind of looping back to the big picture here with James Webb. So this has been in the works for decades. The little dots on this map show where researchers that have worked and still work on specifically the instruments and assembly of James Webb are based. You can see it's a collaboration between 14 countries, Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, Spain, Sweden, Switzerland, and the UK. Did I say the US? The US, of course, as well. And so it's a collaboration also between the space agencies of those countries, so the European Space Agency, Canadian Space Agency, and NASA. A lot of work from a lot of people over a long period of time has gone into this. And so as I wrap up, I'm going to show you one more slide and then a cool video. But before we just wrap up, any questions so far, just to anything that needs to be clarified, and then we can take kind of broader questions at the end. Okay. It's hard. I have to stop like this because if I was in person, you know, I could see it on your faces potentially, but I prefer to make sure that there are no questions as we go. Okay, so this is a not to scale image of where James Webb will go. It's just a geometric image to show you the location. Okay, so this is the sun, this is the Earth, and it's orbiting the sun. James Webb will be on the other side of the Earth from the sun. And so this also helps with cooling down the electronics and all the instruments, as we discussed. But it also means that 2 things, actually a number of things, but two important things. One is that at this location, it's actually feeling, it's weird, but it's feeling the same amount of pull, gravitational pull from both the sun and the Earth. So it kind of just stays there without too much need to use the thrusters to keep it in position. We have to do that a little bit, but not too much. It's basically just gonna follow this line between the Earth and the sun, and it's just gonna orbit along the same orbit. So basically it's gonna have the same orbital period as the Earth. The other thing that this means is that even though this is not really to scale, well, actually it is a little bit to scale in the sense that the distance between James Webb and the Earth is proportional to, as shown here, to the distance between the moon here and the Earth. So you can see that James Webb will be far beyond the orbit of the moon, which means that we cannot go to it to fix anything if anything happens. But that is the price to pay for having, being able to get down to the temperatures of 6 Kelvin, okay, which is really critical to be able to do this unexplored until now science. It's also why, we've taken so long to build it and prepare the launch. We want to make sure that nothing goes wrong. And so let's wrap up with a little video here showing, so you'll see at the top kind of the days ticking by. Notice that it's not just hours, it's going to be the days. And this at the bottom kind of shows where James Webb is as the various things in the video happen. I didn't play the whole video because it's quite long. So you can see we start at a point where James Webb is already way past the moon, but it's going to go a little bit further. And as it does so, it will begin to deploy. Notice that all 18 mirrors are not visible here, all 18 segments, I should say, only some of them or most of them. And it also, the shield hasn't yet deployed. So let's watch.
Hexagonal tennis court size shape.
Oops. Yeah, I'm just going to turn this off. The narration is in context of the larger video. But the main thing to remember here is, well, all the little steps, right? You don't have to remember those for any reason. But the fact that all of this is pre-programmed. James Webb is doing this by itself. It is not something that it will do in response to people pressing buttons. This is all pre-programmed ahead of time, because time delays the time it takes for us to press a button and for James Webb to receive that message and begin doing, I mean, each of the steps, the big steps, will be triggered by people, but overall, it's not going to be micromanaged at a detailed level. A lot of this is pre-programmed and has had to be tested on the ground to make sure it works well. So we saw the shield, right, the sun shield come out. And there it is. And then now we've got the secondary mirror kind of come into place. The little package that I had to fit in a rocket is now expanding and becoming the telescope that we've seen in all of these images. Getting some of the detectors out. And then one of the last steps here is going to be the mirrors opening up. So notice we started at 5 days and we are now at 13 days. Okay, so this is a very slow process. There's no need to hurry because you don't want anything to break. And I said earlier that I was going to tell you another reason why we can't, once it's assembled, it's not designed to put the mirrors back or reorient any of the mirrors. And that's because when you have a telescope that's going to go in space and you know that no human will be able to go and fix it, you have to limit. I laugh as I say this because we've seen a lot of moving parts, but you have to limit the number of things that are allowed to move. So even though we've seen a lot of things move, believe it or not, Hubble and other telescopes on the ground, for example, have a lot more moving parts than James Webb. But basically, once it's assembled, we're only moving the whole thing to point at a star, and that's it pretty much. And small movements inside the optical assembly to change between the different detectors, right? So you can observe with you saw the 4 instruments earlier on. You can choose the instrument you want to observe depending on what it is that you want to observe. And that's about it. The more things that move and that are allowed to move, the more things that can get stuck, broken, caught on something. So you really want to minimize motion once it's deployed. And so reorienting one mirror away or anything like that is not part of the plan because it's way it's way too dangerous. Okay, so with this in mind, I'm going to basically wrap up and take all of your questions. Hey, what happened? Okay, there we go. All right, so I see questions both in the chat and in the Q&A. Right, so I'm glad you asked about where to go next. So tomorrow, I am giving a presentation in person at the planetarium at the New Mexico Museum of Natural History. I think that's right. Yeah. And it's in their calendar as well. And that's at 6 to 8 p.m. And it won't just be me, it will actually be Professor Tony Hall, who has, he owns the company, he's retired now, but he owned the company that polished the mirrors on this thing. Okay, so he has held each one of those mirrors in his hands. Unfortunately, I haven't even seen James Webb in real life. Part of it is because I'm a Canadian citizen, and so they think I'm gonna break it or something. I don't know. It's complicated. I'm kidding, but it's complicated. But yeah, it's quite difficult for even me to see it, and I have not seen it. That's okay. I just want to get the data. But Tony has actually worked on making and polishing and coating the mirrors, and he's going to be talking a little bit more about that, which is, you know, an aspect that I don't know as much about. And he's going to and so that's on Friday, 6 to 8 at the planetarium and the museum, and then Saturday 11 to 3 we're going to have more of an interactive sort of pre-launch party where we're going to have a few booths and we'll be talking with people. I think we're gonna show a couple of these films, the longer versions of them, on repeat in a theater, and I think both museums are free. Both events are free of charge. We'll also have this is my personal favorite, an Oculus VR headset set up so that you can walk and experience James Webb in virtual reality. I loved doing that. I did it a couple of times, and it's amazing. You really get to see the pure size of it, and it's a whole other kind of experience. All right, another question here. Let me first go to Q&A, and then I'll go back to the chat. You guys can see this, I guess, right? All right, what is the fuel source for maneuvering the telescope? I want to say is, well, hydrazine is used often for the thrusters. So I would guess it's the same, but this is one that you might want to double check on Google. The space telescope is not going to power, James Webb is not going to power itself to its location, and that's why it's going to take 6 months to get to that location. It's just going to use the gravitational pull of well, the rocket will take off, but once it gets separated from the rocket, it's not gonna propel itself all the way to that L2 location. It's just gonna use orbital dynamics, so just gravity, to kind of slowly make its way there. Don't want to put too much propellant on board because it's heavy, and that makes the launch even more expensive. But it will have a little bit of propellant, so it can just point and look at different parts of the sky. Okay, if or when your research brings up more questions, will you be allowed more telescope time? That's a great question. It's actually pretty competitive. So if I want to use James Webb, there are 2 ways I can do it. If I want to be first at the data, I have to write an application like for grants, except it's for telescope time. And I have to justify my science really well. And then, you know, lots of other astronomers are doing the same thing. And then maybe for the first year of James Webb, this has already happened. And about 1 in 5 applications were selected. And the other ones were not. Actually, a number of the ones I was involved with were not selected. The lava planet one was. So it's actually fairly competitive. The other way to use the data is that after 1 year of being acquired, I think it's 1 year, it might be a year and a half. I know that they're still kind of debating that for future, for the rest of the mission. After that time, the data becomes public and anyone can look at it. But the caveat is that any cool, interesting stuff will probably have already been published. Then again, I think that there's still going to be a lot that one can do with the data even later. I think we're going to have more data than people to analyze it in some cases. So there are a number of ways that we can access James Webb data, even if the proposal is not selected. And then another question here, will Webb travel beyond this dark side orbit of the Earth? Do you mean, will it leave that spot at L2? I'm not sure. Okay, no, it's gonna stay there. It's gonna stay at L2. And when it runs out of coolant, we're hoping that we can still use it, still from L2, the same way that we have used the Spitzer Space Telescope when it ran out of coolant. Astronomers can be quite intrepid in that sense and find new ways to observe. What are the mirrors made of? It's this element that starts with an M. Oh my gosh. It's next to silver in the periodic table. I keep forgetting the name because it's more morbidium, more something like that. I think it's MD as the formula. And so that's actually not what you see, the golden kind of color. What you see is actually the gold coating on top of the mirrors. So they're coated with a very thin layer of gold. And the reason for the combination of materials has to do with being able to not deteriorate in space. Molybdenum, thank you, yes. To not deteriorate in space, and also to get the right amount of reflectivity for the wavelengths that you're observing at. So if you stood in front of James Webb, you could see a reflection in the mirror, but it may not reflect as well as a visible light mirror like the one in your bathroom, because it's primarily made to receive infrared light. So the properties of the coatings on the mirrors are a little bit different. Gold coating in this case. Okay, let's see. Another question here. Yeah, how might James Webb inform theories of dark matter or dark energy? Well, you tell me. That's a great question, and I think so. It's a little difficult to answer, and the reason is because dark matter and dark energy, especially dark energy, so I keep getting distracted by the little things that show up. Dark energy, especially, we're still not even exactly sure what the best ways are to study it and understand what it is. Dark matter that's also the case, but to a lesser extent. So I'm gonna say that at least for dark matter, we'll be able to understand the way that dark matter was distributed in the universe earlier on by observing how the free-floating stars assemble into galaxies. Dark matter was all around them. We just can't see it because it's dark, right? But by understanding how the stars assemble into galaxies and how the first galaxies came to be and over how long and how they interacted with each other when they were still mixed, by understanding all of that for the first time, we'll have a better sense of the distribution of dark matter gravitationally. And we might be able to say more about what it is that way, or at least constrain some of the models, rule out some other models, basically narrow in more on what dark matter is. Dark energy, I think we will learn new things about dark energy, but exactly how is probably going to be a surprise. I feel like those are the areas where we just don't know what we're going to see. So stay tuned. All right. I'm sorry. Thank you. Yes. I got my, I'm a chemist. All right, cool. So any other questions then? I'm happy to answer. You can also just raise your hand, I guess. And
While we see if there's any more questions, I just want to also thank the Friends of the Santa Fe Public Library for sponsoring this event, and a million times thank you to Dr. Dragomir for providing this wonderful presentation to our community far and wide. I learned so much, and I am so excited about the James Webb Telescope. A million times.
yeah.
for sharing this.
Same here. And if you do want to learn more about my research, I have a website, so just Google my name and you'll see more there. All right. Well, have a great end of the week, I guess, and look forward to check on the launch.
Yeah, thank you. Thank you everyone for attending. Have a great evening.
Bye.